Hey guys, welcome to the next session in this track that will be related to application of Kotlin as a programming language in deep learning space. Let me start from introduction. My name is Izzet and I'm a proud father. I have a son. He is 3 years old and he keeps me busy all my spare time. During business hours, I'm a solution architect working for EPAM in Kyiv, Ukraine. My primary programming language is Java, and recently I was infected by artificial intelligence disrupting power. I'm also passionate about flexible software engineering methodologies, good engineering practices, habits, and crazy about automation. So that's it about myself. Let's move forward to agenda for the session. First of all, I would like to share with you some motivation behind this talk. Why do we need to care about deep learning? Why do we need this? Then we will walk through some key points related to deep learning and artificial intelligence in general. Of course, talking is cheap, so I would like to propose to you to have some coding practice during which we are going to create simple but still deep neural network to learn something to do. There will be some takeaways, so if you're interested, you can go to check out for more details, and I will try to manage time so that you will have a chance to ask me questions. Okay, let's start. Why should we care about deep learning and artificial intelligence in general? First of all, I would like to emphasize that AI is disrupting a lot of things around us. And currently, probably, it's not something remarkable when we say that automobiles are capable to transfer us from point A to point B completely in autonomous mode, without any human intervention. Next thing is, there is a research by BBC. They actually created the list of jobs which might disappear in the nearest future. Those jobs like taxi drivers, maybe cashiers, etc. I believe even what we are doing right now as a software engineers in the nearest future will become less and less useless. Why? Because there is no capabilities for the person to write software that is capable to solve such a complex problems, which actually AI is capable to do. And of course, earnings, actually, there are artificial intelligence researchers in US who actually paid salaries in 7 digits, so more than $1 million a year. This is because of huge demand, and demand is continuously growing. Okay, let's move to some remarkable events from my point of view, which make us think about the power and the capabilities of artificial intelligence. There was an event in 2016 when algorithm called AlphaGo was invented by a company that is called DeepMind, which was acquired actually by Google in 2015, which defeated the best Go player in the world. For those who don't know, Go is actually the ancient Chinese war strategy game, and there are more variances to play than the number of atoms in the universe. There are 10 to the power of 170 variances to play in the Go game. And there are just 10 to the power of 80 atoms in the universe. I don't know who calculated this, but Wikipedia says it like this. And just recent years, they actually invented the next version, the next generation of the AlphaGo, which is called AlphaGo Zero, which was trained without any human intervention. Basically, it was trained without constraint by limit of the human knowledge. It means that Previous version of algorithm was trained by the videos how human with human play in the Go game. New algorithm doesn't learn this. It was capable to learn the Go game from scratch, from zero. And it was actually able to defeat the previous version of the AlphaGo. Next event. Again, last year, non-profit organization called OpenAI implemented the model which was capable to defeat top Dota 2 player. As we know, Dota 2 is, again, the strategy game, and it's not something easy to code, right? To code the algorithm which will be able to survive and actually to win the human in this game. So it's really, really complex game, and it will be really, really hard to implement such algorithm. I believe it's maybe even impossible. So those two events actually make us think about the capabilities of artificial intelligence and what is still capable to, and where it can be applied, and what will be changed in the nearest future. So that's probably enough about kind of inspiration to move forward. But let's stop a bit and take a look at what is actually behind the artificial intelligence and deep learning specifically. First of all, deep learning is a marketing term. I believe it does its job because it attracts many attention, and nowadays it's a kind of buzzword. But underneath, deep learning is just deeply stacked artificial neural networks. By itself, deep learning is a subset of more general machine learning, and machine learning in its turn is a subset of more generic and more common artificial intelligence. Artificial intelligence by itself is the way when machine capable to perform some tasks, but in a smart way. Machine learning is a subset of it, and this is the way how we train machine to do something using the data as an input. And deep learning in this case is just similar to machine learning, but is trained using vast amount of data. Okay, let's move forward. The minimum unit of artificial neural network is artificial neuron. Okay. It's not exactly the same as, for example, neuron of human brain, but it was inspired by by understanding of how human brain's neuron works. For example, artificial neuron has dendrites. This is the same as inputs to artificial neurons, where data is coming to artificial neuron. It has similar body, where actually the computation is happening, and it has synapses or output, which is responsible to move signal from neuron to the next neuron in the neural network. Artificial neural network is actually a network containing of set of neurons connected with each other to conduct some pattern. Usually we depict three common layers. Those are inputs, hidden layers, and output layers. The responsibility of the input layer is to receive the data and to pass it to the hidden layers. Responsibility of the hidden layers is to pass data between layers and to actually learn something from the incoming data. And output just outputs the results of the learning process. Okay, let's move forward. Actually, I believe you know that artificial neural networks were invented not just several years ago. It was there for, I don't know, several decades. But humanity was not believe in them because they were capable to do something, but not too much. But there were several breakthroughs which actually make this happen, and we now believe in more in capabilities of neural networks to do something useful for humanity. First of all, it's a compute power. We know there are lots of breakthroughs in computation power, and now we have lots of hardware resources to do some expensive computations. Of course, there is a data. Maybe you know that just several years, recent years, humanity overall collected more than 90% of data from the whole existence of the humanity. And of course, all this drive the invention of new algorithms or improvements of existing ones to deal with such amount of data and to consume the existing computing power. And of course, infrastructure. So those 4 breakthroughs made happen that now we believe in neural networks. I believe you already started to think, where is the Kotlin? And this is where it is. So my vision that with Kotlin and machine learning is the following. Probably you know that the most common languages in data science and artificial intelligence are Python or R. But there are some advantages of the Kotlin I can see, which might bring some bright future for this programming language. First of all, it's conciseness, because with less boilerplate code, with less ceremony, we can achieve more and faster. Second thing is interoperability. We know that there is actually a talk regarding the multi-platform Kotlin. Maybe some of you visited it. And actually, we know that Kotlin is programming language using which we can write software for different platforms, starting from server for backends, continuing to compiling the Kotlin program to JavaScript and then run it in browser. And of course, we can run programs written in Kotlin on Android or iOS platform. So Kotlin is almost everywhere. And there are some use cases, especially maybe you know that GDPR came to Europe, where we cannot send sensitive data to the backend. So it should stay at the edge. And in this case, such programming languages like Kotlin can be more shinier than other ones because we can train neural network at backend, but then use to infer and to leverage the trained model on the edge devices without sending sensitive data to backends. And of course, accessibility. Using Kotlin, there are much more simpler to create some domain-specific languages for people, for some subject matter experts who are not true to programming. They are not capable to program, but they speak their domain language. And by implementing some domain-specific language, we can leverage their knowledge to invent something new, to create some useful products for us. And Kotlin also shines here as well. Well, token is cheap. Let's do some coding exercise. So the idea behind this exercise is to create neural network, deep neural network, which will learn to XOR operation, exclusive or logistic operation. But to increase complexity of this thing, we will do 3 inputs to the neural network and expect 1 output to learn. So the XOR works the following way. If there is odd number of truths, then the output will be true. If we have, for example, 2 truths out of 3, that means that output will be 0. So pretty simple, but still quite interesting whether AI can do this without any help from the human, so that me. Okay, let's start with some coding. First of all, let's create some simple Kotlin class. Let's call it KNN. And then let's create a test for it. it's so simple. Let's split our screen to vertically so that it's more convenient to work with two classes at the same time. Then let's implement a bit logic. Let's create a function which will be responsible to test our neural network. Pretty simple. Let's have annotation. So nothing special for now. Let's create an instance of our neural network. Here we go. Usually when we train neural networks, we are specifying the number of epochs it should train. Let's specify that it will be 1,000 epochs to train our model. And again, it's useful to debug our neural network to know whether it's learning something or no. And let's define that every 100 epochs we will print something to output. Let's create those fields in our neural network class. Epochs. This will contain the number of epochs, and this will contain how frequently we should print something to the console. Okay, now let's define our input data. Our input data will be according to the rules how XOR function works. So as I already said, odd number of truths creates true as a result. Then let's create expected set of data that our model should learn. Here we go. So we have 4 by 3 matrix, and each row corresponds to particular expected result that our model should learn. So first row gives us 0, second row gives us 1, third row gives 1 as well, and the first row gives us 0. Okay, now we need to train our model. It's simple like this. So basically we will create a function which will fit with input data and expected data to learn by the model. Here we go. The next step is to actually test whether our model is capable to learn something. So let's create assert. Let's say that we are expecting 1 for the input to our neural network. That will be something like, let's use the second row. This is 0, 0, 1. Okay, and let's create the test method within our neural network class. This should return matrix of double, and let's return 0 for now in order to make sure that our test expected test return. Yeah. Okay, so here we go. Let's run our code. It should fail, right? Because we are returning 0 while we're expecting 1. Okay, next thing we need to do is to fix the randomness of our neural network, and by setting seed to constant value, it means that every time we run our neural network, it will produce by random algorithms the same values. Next steps is to initialize the weights for our neural network. This is the thing using which the neural network is capable to learn something. I will explain it a bit later. Let import comma extensions to have this cell working. Let's create one more layer because we will have deep neural network. It will contain 3 layers and 2 weight matrices to contain to connect input layer with hidden layer and hidden layer with output layer. Here we go. So first weight matrix will contain 3x4 matrix, and the second weight matrix will be 4x1 because our input is 4x3. So after multiplication of matrix, we'll have 4x4 matrix, and then the XOR actually produces the binary output, which means that we need one value as an output. Then it means that we need to create 4x1 matrix to at the end to have 1x1 matrix as a result of calculation of our neural network. Then let's train our model. For number of epochs we defined, and let's create the first layer. It will be simple like this. So that's it. This is our input layer of the deep neural network. Let's create the second layer, which is also a hidden layer of our neural network, which will actually which will do some computations, and it's a bit more complex compared to the first layer. And this is the way how actually neural networks are capable to learn something. Basically, we multiplying our input by weight and then passing these results through activation function. Let's create this activation function, and in a minute I will explain why do we need activation function. A matrix of doubles. Okay. So activation function is the thing that brings nonlinearity to the neural network model. This is the thing that makes our neural network to learn different functions. When we are initializing our weights with random values, and after each iteration, these weights values will be updated by some small derivative value calculated based on the activation function computation. It will, at the end, learn some particular function how to approximate given input to expected output. In our case, we will use a sigmoid activation function. This is one of the simplest one with some drawbacks. But the main idea of sigmoid is to keep values between 0 and 1. And we know that our binary classification is actually output can be 0 or can be 1. There are different activation functions that are employed in different neural network architectures. Usually, nowadays, most of the time, we are using ReLU for hidden layers because it has some advantages compared to sigmoid or hyperbolic tangent because the gradient is not vanishing. When we, for example, if you're talking about sigmoid, when the value for this function is quite big, then the gradient is quite small. And this slows down the learning process of our neural network. So we implemented here the sigmoid activation function, and let's implement this output layer of our neural network. It will be similar to the previous one, but as an input, we will have the output from the previous layer. So that's it. We actually implemented one of 3 key algorithms of the neural networks, so-called forward pass or forward propagation. Next step is to compute gradients or derivatives of the functions that we applied. So let's calculate it. Let's start to calculate gradients. This is so simple. So basically, at the end of computation, we have L2. This is the result of computation of our neural network. In order to understand is this correct or not correct, we need to find out the difference between expected output, which is Y, and the produced output by our neural network, which is L2. Then let's debug something. So the idea is pretty simple. Each number of epochs will print the errors that our neural network is producing. Let's run our test in order to verify how our neural network is performing. We can see that it performs pretty bad because it doesn't learn anything. And here is actually the time to finish implementation of calculating the gradients, to update our weights, and to implement then the backward propagation for our neural network. In order to do this, let's use the error that is produced by our neural network, and let's calculate the derivative. Here we go. So basically, we are scaling this error by the derivative, which is computed based on what calculations are happening inside our activation function. And all this logic will be inside this activate dx, which will actually find the derivative of our sigmoid. Derivative is a standard thing for different functions, and in case of sigmoid, it's just x multiplied by 1 minus x. Okay, so we have calculated derivative for the second layer, and now we need to calculate the error for which the hidden layer is responsible. In order to do this, we need to find out the scale of the weight matrices of which connected the hidden layer with the output is responsible for the error. So this is done like this, and this is the way how we are calculating the derivative of the first layer by again by scaling the error of this layer by the result of derivative of activation function. Here we go. So let's try what's happening with our model. Nothing is actually happening because we just finished the implementation of calculating the gradients for our neural network, and then the main thing is backward propagation, where we will use those derivatives to update our weights. So imagine the situation: we have kind of 1,000 iterations. We initialize our weights randomly, and then after each iteration, we have some small value to update our weights, so that in the next term, in the next iteration, the multiplication of input by the weights will produce slightly different value, but it will be more closer to what we're expecting. And then with thousands of iterations, at the end of the day, we will have a model which is capable to approximate the given input to the expected output. So let's see what will happen. Let's update our weights. So let's update one of our weights, the second one. Let's run our test one more time in order to see are there any differences in the outputs that we have. So we can see that our neural network has started to learn something because error is started to decrease. After the first 100 of epochs, we have 0.34, and after the 1K of epochs, we have 0.13. It means that our neural network started to learn something from our input to produce the expected result. Okay, let's close the loop, because we have 2 layers and 2 weight matrices to update in order to learn more from the given input and to produce the expected output. So this is the way how we will update. So basically, we will update our weight matrix by the scale of the output of each layer by the derivatives that we calculated at steps before. Let's run our neural network, and it fails again, and here's why. Actually, we can see that the error is decreasing, and after the 1K of epochs, we'll have 0.03. So actually, it's doing pretty good, but still failing, and this is because actually we didn't implement our test function. So let's fix this, and this is actually how we can leverage what our model learned from the input and by producing the expected output. So we're just reusing the weights and performing exactly the same operation. So basically, input times weight at the bias, we didn't do this, and then pass this value through activate function. So then we have this L2 value, and we then need just to make a prediction. As we know from this slide that sigmoid function is producing the values between 0 and 1. So it can be something in between, whether it's like 0.1, 0.2, up to 1. And we need some kind of approximation. If it's above some threshold, it will be 1. If it's below this threshold, it will be 0. So in our case, if the value produced by the neural network is more than 0.3, then we treat this as 1 or true. Otherwise, it is 0. Let's run our test, and let's see what will happen. Here we go, our test passed. This is actually a pretty simple thing, because our test is actually reusing the data that we are used to train our model. And it's a bit unfair, because it's quite easy for model to have a bias or to overfeed the given training set and to remember how to produce for the given input the expected result. But let's do a little bit more complex for it, and let's feed to it some values that were not present from the training set. For example, as we can see, there is no 3 ones in our training set, but now we're expecting our model to output 1. And we can see it passed successfully, right? So it means that based on thousands of epochs running through data set, by learning how to calculate XOR, how to handle XOR function, it was capable to understand how to produce the expected result for the given input. Let's do a bit more. Let's set, for example, we have something like this. Again, this input was not present in our training data set, which means that our simple but still deep neural network was capable to learn the XOR function completely. Okay, that's it about coding exercise. But is this enough? Of course, no. We saw how we implemented from scratch the 3 key algorithms that are behind the neural networks, how they're actually working. But in reality, we do not want to implement every time from scratch, right? We need something ready, something useful to use in production. We also didn't touch how we actually feed the data to our neural network, because our data set was kind of synthetic and it was quite easy to learn from. Of course, in reality, we have much more data, and we would like to spread our learning process between several machines, some cluster, in order to have more complex problem to be solved by neural networks, and not to wait for this for the long time. And of course, consuming of GPU power, because the operation of matrix multiplication is something that GPU are much more powerful to do, because there are many cores which are capable to perform such operations, and as we can see from the architecture of neural network, this actually the things that can be paralleled, and we can calculate all those matrix multiplication concurrently. So, what are the logical next steps? Actually, in Kotlin ecosystem, there are frameworks that are ready to be used to be applied to the machine learning space, to deep learning space, in order to solve more complex problems that we are capable to solve through the Kotlin. There is a library called Computation, which is written in Kotlin for the JVM. It supports computation using CUDA. CUDA is something that CUDA is the architecture of NVIDIA's GPUs. So basically, we can use NVIDIA's GPUs to perform the training of neural networks. It provides already implemented neural networks architectures, for example, convolutional neural networks, to apply it for image recognition, or to learn something from sequential input, where we can apply recurrent neural networks, etc. Also, there are already implemented activation functions like relucid models of max, etc. And there are functions for calculating the loss and to optimize, to perform the gradient descent, or updating the weights of our neural networks. So everything is already there. We can just use it and to apply to our business problem. Another framework is called Kotlin NLP. Again, its focus slightly different. It's more narrow. The main focus is on understanding the natural language, how we can apply neural networks to understand natural language. And it provides lots of things for this domain, like tokenization, categorization, parsing of entities and recognition, etc. And all this is based on and written in Kotlin. There are some references. Actually, the comma library, this is the thing which are used through the demo. So basically, this DSL is written in Kotlin. So basically, this matrix multiplication written in Kotlin, this one, so this generation of weights randomly also implemented in this comma library. And as you can see, this is actually DSL, right, which makes to write things much more easier comparing to Java. Actually, I started this talk, I tried this talk to write in Java, and I just failed because it's just crazy. Then there are some links. Kotlin data science resources. There are a set of links to frameworks, to libraries, to articles related to machine learning, data science, and how Kotlin can be applied there. There is a link to one of my talks related to artificial intelligence, how to actually get started with artificial intelligence, where to get information from, etc. And there is a source code, the last link, for the demo of this talk. So if you are interested, you can check it. And there is actually comparison of how to write similar neural network in Python, and it's almost like without no differences. And there is application of computation here as well. Okay, some takeaways. So maybe not so practical, but still things that I believe should motivate us to learn a bit more from artificial intelligence, because as I already said, this is something that we have to do, because using like programming skills that we have right now won't help us to solve much more complex problems that we'll have in the nearest future. So disrupt ourselves with artificial intelligence skills to not being disrupted and to stay aside. Artificial intelligence, as we can see, is not rocket science, because this is pretty simple concepts. Again, in reality, maybe it's a bit more complex, but under the hood, it's relatively simple to understand. And right now, there are lots of different sources to get information from, to learn something new. And even I mentioned some quite remarkable events. It's still unbelievable what is possible to implement with AI, where we can apply it with success and to change lots of things that we are used to around us. So thank you for your time and attention. And I believe this is a time for the question. For the questions, how many time we have?
Thank you very much for your presentation. I have two questions, one general and second more detailed. So in general question, did you make comparison performance, for example, frameworks in Kotlin and, for example, with deep learning for G and with some Python libraries? And the second question, in your example, you show that threshold was 0.3, but I think sigmoid function is symmetric in the point 0.5. Why do you use 0.3?
Just the values that was working. We can maybe try to put it at 0.5. I don't think the situation will change too much. Regarding the first question, I believe it's, for the moment, it's unfair to compare those kind of modern and new libraries to what we have in Python ecosystem, because data science in Python ecosystem was kind of started and was developing for a long time. But Kotlin is a relatively new and modern language, but I believe it will have the bright future because of the things that I was mentioned through my talk. Thank you for your question. Okay, anything else? 2, 3, 1. Okay, thank you very much.
Thank you, Izzet, for an awesome talk. And we now have a coffee break. Yep. We're waiting you in 4:20 here for a talk about Apache Beam.